Good morning and welcome to another fun-filled chemistry lecture. Today we're going to be going over the beginning of chapter 13, first half, sections 13.1 to 13.4. This is lecture number 5, and today we are learning about solutions. So what is a solution? What parts are made up, or what makes up a solution? How a solution differs from a colloid or suspension. We're going to be looking at entropy and enthalpy, two thermodynamic quantities, and seeing how those quantities affect our solution formation. We'll also be using intermolecular forces and intramolecular forces to determine if a solution will be made from those. We'll be looking at the difference between a solution and a reaction, and we'll be looking at the idea of equilibrium and how it applies to a solution process. So bringing back the equilibrium in basically every chapter this semester. We'll be looking at how we can change or affect our solubility using temperature and pressure, and how different phases of matter are going to be affected by temperature and pressure differently. We'll also be looking at Henry's law when we're talking about gas solubility. Lastly, we're going to be looking at some concentration calculations, specifically molarity, molality, mole fraction, percent composition, parts per million, and we'll also look at parts per billion. And then we will need to be able to do those calculations as well as interconvert between those different concentration calculations. So let's get right into it. Let's start talking about our different types of mixtures. So last semester we talked about homogeneous and heterogeneous mixtures, and we're going to go into those a little bit more in detail today. So we have homogeneous mixtures, which include solutions and colloids, and then we have a heterogeneous mixture called a suspension. They differ in their components and their particle size and appearance, so let's look at those. The major component within a solution is a solvent. For both a colloid and a suspension, it's going to be a medium. With our minor component, we call it a solute within a solution, we call it a colloid in a colloid, and we call it a particle in a suspension. The particle size of the solute is less than 1 nanometer in a solution. The colloid is 1 nanometer to 1 micrometer, and then a particle is greater than 1 micrometer. Particle size could describe our molecule size or ion size, or it could talk about agglomeration of molecules or ions if we don't actually have solubility. So in the case of a colloid or suspension, we don't have solubility. So what we have instead are these little agglomerations of molecules or ions forming either a colloid or particle based on their size. With the solution, we actually have a dissolving process going on. So making a solution is based on the molecule size as well as whether something is soluble or not. When we think about the appearance for a solution, we're going to have a clear, transparent, and homogeneous solution. So it's going to be clear, not necessarily colorless though, and it'll look all like one thing, so homogeneous. With our colloid, we're going to have a cloudy appearance. It may be significantly cloudy or just somewhat cloudy, but there will be some cloudiness about it. It will still, however, be homogeneous, so you'll only see one substance throughout. With our suspension, you'll have cloudy, usually significantly cloudy, and you'll have a heterogeneous view of this. So you'll see at least 2 substances within here, maybe multiple. Solutions are going to be the most important for chemistry, so we're going to focus mostly on that, although we will look a little bit more at colloids in the next lecture. So a solvent, that is what is a major component of the solution. So it's going to be in larger quantities, and we would say that it dissolves the solute. The solute, or solutes, we can have several, is going to be the minor component of a solution and is dissolved in smaller quantities, and it is said to be dissolved by the solvent. Solution itself is a homogeneous mixture where the composition is same throughout the entire solution. So you can take any portion of that solution and the composition or the actual concentration will be the same for your solute within the solvent. During this, we are not doing a chemical change. We are not changing the chemical makeup of our components. There is no chemical change that goes on, so you're not going to see any sort of like smoke or difference in pH or anything like that. What is changing sometimes is our physical properties, specifically colligative properties, which again we'll talk about next time, but that's the only physical property that should change, is a colligative property. There is a note that I want to make real quick. A solute does not have to be in the same physical state as a solvent. However, the solution will always be in the same physical state as the solvent. So whatever you're dissolving in your solvent, the solution will be the same physical state as that solvent. We can have solutions in all three states of matter. With a gas, as a solvent, it can only be a solvent if we have a gas solute, and that's the only one where we have kind of restrictions. But air, the air we breathe, is considered a solution where we've got different types of gases dissolved in nitrogen. We can also have a liquid solute with a gas solvent, such as Coca-Cola, where we have carbon dioxide dissolved in water and other things, or oxygen dissolved in blood. Solid solute or solid solvent, gas solute, H2 gas and palladium metal. That's common in hydrogenation reactions, such as when we're making tasty, delicious peanut butter. Liquid solute, liquid solvent, stuff like beer, where we have ethanol dissolved in water, antifreeze, ethylene glycol dissolved in water. Solid solvent, liquid solute, mercury and gold, water and salt. Solid solute, liquid solvent, that's very, very common, dissolving some sort of solid. Kool-Aid, dissolving sugar in water. Salt water, dissolving salt in water. All sorts of solid solutes, liquid solvents. And then last, solid. We call this a solid solution. We looked at this last time. And these are going to be our alloys. Right? So from chapter 12, a little bit of review. Stuff like brass, pewter, and stainless steel would be examples of solid solutions, or solid solute, solid solvent. We generally talk about solubility when we're talking about solutions. So how readily something dissolves is its solubility. Solubility is specific to the solute, specific to the solvent, and it's specific to the temperature. So solubility itself is the maximum amount of solute that can be dissolved in a given amount of solvent at a specific temperature. Now, as a note, everything will have some solubility, but it may be very, very low that we basically consider it insoluble. So you may have 1 or 2 particles, so like 1 part per trillion, but you will have some degree of solubility. Okay, let's check in and see how we're doing with our concepts so far. So what are the major and minor components in the solution? Colloid and suspension. Also, what are the differences between the 3 mixture types? So with a solution, we have a solute dissolved in a solvent. With a colloid, we have a colloid dispersed, not dissolved, dispersed in a medium, and it is homogeneously dispersed. And then we have a suspension, which is a particle dispersed in a medium. Okay, what are the differences between these? First of all, particle size. Our solution, the solute will be small, but less than 1 nanometer. Then we have our colloid, which would be 1 nanometer to 1 micrometer, and then our suspension with the greatest particle size of greater than 1 micrometer. Also, the look will be different. With a solution, it's going to be clear or transparent. A colloid and suspension will both be cloudy, and then where our colloid and our suspension differ is that the suspension is heterogeneous, so we would see the different components of our mixture. Okay, so we talked about enthalpy many times, but we haven't really talked about entropy yet. Entropy is the amount of randomness in a system, or the amount of disorder. Greater disorder, greater entropy. And nature or natural systems are going to favor greater disorder. We want disorder. It's something we want. Mixing substances is going to cause more randomness or more disorder. And it's because the position of the molecules are not going to be in this rigid arrangement anymore. They're going to be mixed throughout in a random distribution. This is going to increase our thermodynamic quantity, entropy. So the formation of solutions is favored by the increase in entropy that accompanies mixing. So anytime we make a solution, our entropy is going to increase because of the increase in disorder. So energetically, it's favorable to have more disorder. Okay, let's look at the enthalpy, or the energy involved in dissolving. So we have to, in the dissolving process, the first thing that's going to happen is we're going to drop a solute into a solvent. During that time, that's going to cause our solvent particles to get pushed apart. Then, after that occurs, our solvent is going to come in and start to separate our solute particles. After that, our solvent particles are going to surround our solute particles. So, comes in, then pushes apart our solvent, then the solvent comes in, pushes apart our solute, and then we have a process where our solute and solvent interact. So here's sodium chloride, and this is the interactions that we form. So we have water that comes into contact with the sodium ions and the chlorine ions, and that, hopefully we remember from chapter 11, is called an ion-dipole interaction. So each of these processes require energy or release energy. Whenever we're breaking electrostatic force, this requires energy. So breaking solute-solute interactions, breaking solvent-solvent interactions requires energy. And then as we make new electrostatic interactions, that's going to release energy. It's going to be an exothermic process. So making these ion-dipole interactions releases energy. So when we're thinking about making a solution, we have to think about the energy that's associated with breaking and making new electrostatic forces. As a note, hopefully you learned this in 1211, but let's go over real quick how compounds that are covalent differ than ionic when we're dissolving. So covalent compounds themselves, such as sugar, we're breaking intermolecular forces, and we're keeping our molecules intact. So we're not actually breaking anything apart besides intermolecular forces. This is called solvation. So anytime we have a solvent molecule surrounding an iron or molecule with intermolecular forces, we call this solvation. If that solvent is water, we call it hydration. And that's irregardless of whether it's covalent or ionic. When we're dissolving an ionic compound, our solute molecules are going to surround individual ions. So they break down the ionic solid into ions. So there is nothing's left intact, it's just ions. Granted, it was made up of ions, and we have to break those electrostatic forces to make new forces between our ion and our solvent. So the water itself collides with the edge or corner of the solid until we break free individual ions, and then those ions are stabilized by water, forming ion-dipole interactions. So, instead of having our water bonding with itself, the hydrogen bonding, we have the formation of ion-dipole interactions, which is a very energetically favorable process in most cases. Okay, so let's look at the energies a little bit more in detail. So we've got our solvent-solvent interactions, intermolecular forces between solvent molecules. Unless we're talking about a solid solvent, in which case it would be intermolecular forces. So we have to overcome these in order to disperse the particles. So usually it's going to just be intermolecular forces that we're breaking. And then we have solute-solute interactions. This could be intermolecular forces or electrostatic interactions such as ionic bonds. And these also must be overcome in order to make room for the solvent. Lastly, we've got our solvent-solute interactions that will form after mixing. and these are going to be intermolecular forces between our solvent and our solute molecules. And these interactions occur as the particles mix. So what happens, or when are we going to actually form a solution? Anytime we have a gas, mixing gases is a spontaneous process, so a gas solute will always dissolve in a gas solvent. We don't have to think about it energetically. It's a spontaneous process. Entropy tells us it's going to happen every time. Remember, with gases, we don't have intermolecular forces, or we don't worry about intermolecular forces with gases, so that's taken out completely. All we think about is entropy in that case, so no enthalpy coming into account here. And remember our Dalton's law. Each gas acts as if it's alone to fill the container, so we're going to bring that back up during this lecture. Other states of matter, we have to think about solvent-solvent interactions, and they have to be similar to these solute-solute interactions in order for a solution to form. So we think of a like dissolves like mentality. Polar dissolves polar, nonpolar dissolves nonpolar, ionic is dissolved in polar. So we want to have similar intermolecular forces, and our structure itself will determine our intermolecular forces. So remember chapter 11. And those intermolecular forces will affect the extent of solubility. When we have solute-solvent interactions forming, these are going to, when these form, if they are much weaker than our solvent-solvent or solute-solute interactions, we're going to have a case where we have our delta H of solution, the energy that is going to be absorbed or released during solution formation. It's going to be very large and positive. This will not be energetically favorable, and therefore the solution will not form. So if we have a delta H of solution that is positive, more positive than the entropy can account for, then we will not form a solution. Here's just a breakdown of our energies associated with solution formation. So in both of these cases, we have the ability to make a solution, whether it's exothermic solution formation or endothermic solution formation. Again, it's just a balance of those energies. So we've got to break down our solvent interactions. We call this delta H1. Then we break down our solute interactions. We call this H2. And then we form our solute-solvent interactions, or our solution interactions. We call that H3. If we have an exothermic process, our endothermic processes will be less than the exothermic process of making our solution. So we have a delta H that is going to be negative. So heat will be released. If we have, in the case of an endothermic process, we've got our endothermic processes being greater than the exothermic solution formation process, and we'll get a delta H that is positive. So heat is absorbed. And as long as this is small, we will still make a solution due to the entropy that we gain during this process. So it's a balance of energies, and we'll look a little bit more at that balance in just a minute. So let's look at water dissolving salt and water and oil and see how these differ energetically. So first thing we do is we need to separate out our sodium and chlorine ions, and we need to separate out our water molecules. So when we separate sodium chlorine, we're breaking intramolecular forces, so we're breaking ionic bonds. When we're breaking up our water, we are separating water molecules or breaking hydrogen bonds. After that, we are going to make ion-dipole interactions, and that is going to be highly exothermic. But overall, when we dissolve salt or sodium chloride in water, this is actually an endothermic process. So it's a little bit of energy that's required. So you actually, if you make salt water, you actually feel it get a little bit cold. But since this is so small, we can overcome this with entropy. So we will still make this solution. Now let's think about how this differs between oil and water. So first, we're going to separate our oil molecules. This is going to be breaking London dispersion forces. Then we're going to separate our water molecules, breaking hydrogen bonds, and then we're going to make dipole-induced dipole interactions. And this is going to be not very energetically favorable. there's not a lot of energy that's gained during the making of ion or induced dipole interactions. So that's not very exothermic process. It's not even as exothermic as forming new hydrogen bonds. So this will not be a very energetically favorable process. Here we're going to have a delta HF solution that is highly positive. So it is very endothermic, and the solution will not form because of that large positive delta HF solution. As I said, we can still have endothermic processes. We just have to have that endothermic process not be that great. We take advantage of endothermic processes whenever we're using a cold pack. So instant hot packs and instant cold packs, you break them or you squeeze them. And when you do that, you break something inside that releases a solvent or a solute. And as it mixes with the other component, you have a solution form. When that solution is formed, it is either exothermic, in the case of an instant hot pack, or it's endothermic in the case of an instant cold pack. Again, we can still have solutions formed if it's endothermic, and we take advantage of that when we're using an instant cold pack, but it just can't be very large. So in the case of a delta HF solution that is negative, our solvent-solute interactions are dominant. If it is positive, our solvent-solute interactions are not dominant. It's going to be solute-solute or solvent-solvent. Okay, so let's look a little bit more at the energy. So whenever we're thinking about if a solution will form, we have to think about a quantity called Gibbs free energy. So it takes into account both enthalpy and entropy. So enthalpy and entropy come together in this equation where we have delta G, or Gibbs free energy, equaling our change in enthalpy. So that is based solely on making and breaking intermolecular and intramolecular forces. And then our entropy, so minus temperature times by entropy, where entropy is going to be positive in any solution process. If we have a negative delta G, that means we have a process that is spontaneous, and we will have a solution form. So in order to have a solution form, we have to have a negative delta G. Also, as a note, delta G is a state function because of the two thermodynamic properties that make it up are also state functions. So the heat energy that we're looking at our delta HF solution, where we have our solute-solute, solvent-solvent, and solvent-solute. So remember, any like dissolves like is usually going to be negative, so it's going to be a favorable process. And again, when we have our solute-solute or solvent-solvent, this requires energy. Our solute-solvent releases energy, and we have to have that large enough to have an energetically favorable process, or at least after we take into account entropy, that it'll be energetically favorable. Entropy itself is always going to be positive in a mixing process. Okay, let's see how we're coming along with our learning objective. So we've got 3 substances. Those 3 substances are lithium chloride, benzoic acid, and naphthalene. And we're going to be dissolving them in water, or at least trying to. From this information, we want to know which one do we think is going to be the most soluble, which one do we think is going to be the least soluble based on enthalpy changes, so enthalpy alone. So our different solutions. That we're going to try to make are lithium chloride in water, benzoic acid, in water, and naphthalene in water. What we need to look at are our solute and solvent-solvent interactions. And then we're going to look at our solution interactions. And from there, determine what our delta HF solution is. First, lithium chloride in water. We're going to break ionic bonds and hydrogen bonds. When we make our solution, we're going to form ion dipole interactions. And our delta H of solution in this case should be negative and medium-ish, because we're breaking ionic bonds, so that does require energy, and we're breaking hydrogen bonds, which requires energy, but ion dipole interactions are fairly strong. Then we've got benzoic acid and water. With benzoic acid, we have hydrogen bonds, and with water, we have hydrogen bonds. Benzoic acid looks like this. So the hydrogen bonds in benzoic acid will not be nearly as strong as the ones in water. We will be forming new hydrogen bonds, and this will probably also be negative, but probably a little bit smaller than the lithium chloride. Lastly, we're going to have naphthalene in water. So we're breaking London dispersion forces with the naphthalene and hydrogen bonds with the water. We're going to be making dipole, induced dipole interactions. And that is a very, very weak interaction, significantly weaker than our hydrogen bonds. So this is going to be a positive process, which means this will probably be, the lithium chloride will probably be the most soluble, while our naphthalene will be the least soluble. And the only reason that our benzoic acid is not the most soluble is because with benzoic acid we have a lot of nonpolar interactions going on as well, and we just have a little bit of the molecule that hydrogen bonds. So the hydrogen bonding that we're going to get back is not going to be nearly as significant. Okay, so let's look at our difference between dissolving and making reactions, or doing reactions. So dissolving, we're not changing anything. We just have a process where they're interacting and attracting each other, but they're not changing their identity, and this is considered a reversible process. We should be able to get back out the components of a mixture just by physical changes. A reaction, though, is a chemical change and involves the rearrangement of a molecular or ionic structure. So this is not a physical change or a nuclear reaction that's going on. Our chemical identities are changing in this case. And generally this is considered irreversible. So the big difference between the two is whether they are reversible or irreversible. And then do we retain the same thing, or are we making something new? So let's see if we can take that idea and put it into action. So a sugar cube dissolved in hot tea. We dissolve sugar in hot tea, we still have sugar. We've just broken the intermolecular forces holding the sugar cube together, so this is going to be dissolving. SO3 dissolving in water to produce sulfuric acid. When that occurs, we make something new. So this is going to be a reaction. And then lastly, calcium oxide dissolving in water to produce a basic solution. If we are producing a basic solution, that means we have produced something new. So this is calcium oxide, right? That is not basic. Basic means we have hydroxide ions. So during this process, we've produced hydroxide ions, so this is a reaction. Okay. We can characterize solutions based on how much solute is dissolved in solvent. We have what's called an unsaturated solution. That's when we have less solute than our equilibrium solubility. So this means we can add more solvent in. So we have not reached equilibrium yet. We can add more in. So more solute itself will dissolve in your solvent. If we have a saturated solution, we have an equilibrium process going on where undissolved solute is in equilibrium with the dissolved solute, and this is where we have the maximum amount of dissolved solute. In this case, we cannot add any more. So no more will dissolve. So we are at a system at equilibrium. And then we have what's called a saturated solution, so a solution where we have more dissolved solute than solvent. And in this case, we have something where we have kind of forced this to occur. You usually are going to heat this up. So as you increase temperature, you're going to increase the solubility, and then you let it cool slowly without any disturbances. Once you disturb it, you're going to actually cause the solute, or the excess solute, to crystallize out of solution because we are not in equilibrium. So let's look a little bit more at this equilibrium process that's going on. So two processes occur. We have our solute plus our solvent, and it's going to have the solute dissolved in our solvent, called dissolution. So our solvent particles are colliding with our solid solute, causing the solute particles to interact and dissolve, detaching from the solid and dissolving. We also have crystallization, so when two solute particles crash into each other, they're going to recrystallize because they have reattached and crystallize out of solution. In a solution, both of these processes are occurring. So let's see. What two processes are occurring when we're forming a solution? Hopefully you saw dissolution and crystallization. When these are in equilibrium, we have a saturated solution. Okay. Now let's look at our factors affecting solubility. Of course, one of the big ones for anything besides gases is going to be intermolecular forces, because the intermolecular forces are going to tell us whether a solute is soluble in a given solvent. However, we can affect solubility using surface area, temperature, and pressure. Surface area itself won't determine the degree of solubility, but it will determine the speed of, or the rate of dissolution. And then temperature and pressure will be dependent upon phase. So let's look at our different phases of solute and solvent. So if we have a liquid solvent with a solid solute dissolved in, when we think about temperature and solubility, as we increase that temperature, we're going to increase the solubility. So what happens as we increase the temperature, we have more collisions on the solid surface, leading to faster dissolution and more dissolving. We don't have crystallization occurring quite as much. Since they're moving faster, they don't have the ability to form and attach. Pressure, no effect whatsoever. With surface area, even though our solubility itself doesn't change, our rate of solubility increases because we have more surface area in order for collisions with the solid surface to occur. So we have a greater rate of dissolution. With liquid-liquid, so liquid solute, liquid solvent, there's going to be no effect with any of them, or very little impact on miscibility, which miscibility is the liquid form for solubility. There will be little impact of temperature, pressure, or surface area. If we have a gas solute with a liquid solvent, if we think about temperature and solubility, as we increase temperature, we're actually going to decrease solubility. And the reason for this is because now we have faster moving gas particles. Faster moving gas particles are going to be much more likely to escape the solution. Okay, what about pressure? So what happens as we increase pressure? If we increase pressure, we're pushing the gases back down into water. So for water, gas solubility is going to increase. So looking over the right, we've got schematic. So we have equilibrium going on with solubility of our gas particles. We increase the pressure. It's going to cause those gas particles to get pushed into solution. So the more force, the easier the gas molecules can penetrate the liquid surface, so they'll enter the solution, and the harder it is for those to actually exit the liquid. As a note, if we have a non-aqueous solvent, the solubility of the gases will increase with increasing pressure. So for water, we have this curve. However, if we have a non-aqueous solvent, we will increase gas solubility with increasing temperature. So the pressure solubility relationship of gases is related using Henry's law, where solubility is equal to Henry's constant, Kh, times by the pressure. Kh is a constant. It's specific to a gas, a liquid, and a temperature. So the only thing we can change is our actual pressure when we're dealing with K. The P is going to be the partial pressure of the gas, remembering that the P of the gas is equal to P of the atmosphere times by the mole fraction of the gas. So remember that from back in 1211. The equations can be rearranged in order to look at pressure and solubility of a gas at two different conditions. S1 over P1 equals S2 over P2. So as long as we keep temperature and gas identity the same, we can use this relationship. Okay, so let's try and use Henry's law. We've got oxygen. That oxygen is dissolved in 80 liters of, we're going to call it water in that aquarium. The total pressure is 1 atmosphere, and mole fraction is 0.21, with a Kh of 1.3 times 10 to the negative 3 molarity over atmosphere. So we want to solve for our solubility, and it'll equal our K constant times by the pressure of oxygen. To figure out our pressure of oxygen, it's going to be our atmospheric pressure times by our mole fraction, giving us 0.21 atmospheres. That can then be put into our equation. So we have our Henry's constant, and we're going to multiply that by our partial pressure of our oxygen, and that gives us 2.73 times 10 to the negative 4 molarity. So now we know what our solubility concentration is for oxygen within our water at a specific pressure. Now we need to take that and we need to convert that from molarity into grams, because it asks for the mass of oxygen. So we're going to go, since we have a volume, we can take our molarity times it by our volume to get us our moles of oxygen. That gives us 0.0218 moles of O2, and then we can convert that from moles to grams using our molar mass. And that gives us 0.70 grams of O2 dissolved in that 80 liters of aquarium. Okay, we're going to look at our last topic, concentration. So concentrations, we generally talk about the amount of solute dissolved in a total volume of a mixture. That is not always true. You're going to see one case where it is not, specifically molality. But molarity, that is true. We have moles of a solute in liters of solution, moles per liter. That should be a review. However, a new one, molality. Concentration expressed moles of a solute over a mass of solvent in kilograms. This is solvent, not solution. So this is one of those funky ones. This is the only one we need to keep in account, that this is going to be solvent, not solution. Almost every other concentration you're looking at a amount of mixture or solution. So keep that in mind when you're thinking about molality. We also have mole fraction, which again should be a review. Mole fraction is going to be the moles of component 1 over the moles of the mixture, so N1 over NT, and we show it as chi, this kind of funky X. And then we have mass percent. So we have a mass of a solute over total mass of solution times by 100. These can be in grams over grams times by 100 or kilograms over kilograms. Just as long as you keep them the same, they'll cancel out, times it by 100, and your unit will be just percent. Then we have parts per million or parts per billion. Parts per million, you take your mass of your solute over your mass of solution times by 1 million. Parts per billion, mass of solute, mass of solution times by a billion. In this case, as long as your solute and solution units are the same, it doesn't matter what units you use. So just keep them the same and it won't matter. Okay? So, let's try determining parts per million for students in this class versus people in Georgia. So, as long as we keep the unit the same, so we have 50 people, and we have 9.83 times 10 to the 6 people. So we have 50 people in this class. What part per million is the number of people in the class versus the number of people in all of Georgia? So we'll take number of people divided by number of people times by 1,000,000. We multiply this out. We get 5.09 parts per million. Very simple. Okay, let's see if we can kind of cross different concentration units. We have got an aqueous solution of antifreeze, which is ethylene glycol, in water. It's 40% mass percent, and we have a density of 1.05 grams per milliliter. We want to use this information to calculate our molarity, molality, mole fraction. Okay? So, we're starting out with a concentration, 40.0%. When we divide this by 100%, we get 0.400 grams of ethylene glycol, which I'm just going to put as EG, over 1 gram of solution. Okay? Now from here, since we have our molar mass and we have our density, we can go into molarity. So we're going to take 1 mole of ethylene glycol, has a mass of 62.07 grams, and we're going to say that our solution, 1.05 grams per milliliter, and then convert it into liters, 1,000 liters, or sorry, 1,000 milliliters per liter. Multiply that out. And we get a molarity of 6.77. Because now, if we look, we cancel out grams of ethylene glycol, grams of solution, milliliters of solution, and we're left with moles of ethylene glycol per liter of solution. Okay. We can also say, okay, if we have 1 gram of solution, we have 0.400 grams of ethylene glycol. So we take the fact that our total solution volume is ethylene glycol plus water, we'd say 1 gram minus 0.400 grams gives us 0.600 grams of water. Okay? So we can take that idea, 0.400 grams of ethylene glycol per 0.600 grams of water, and we can get to molality. So we're going to go from grams of ethylene glycol into moles of ethylene glycol, and then we're going to go from grams of water into kilograms of water. So 1 mole of ethylene glycol has a mass of 62.07 grams, and then there's 1,000 grams of water per 1 kilogram of water. We'll cancel out our grams of ethylene glycol, cancel out our grams of water, and be left with moles of ethylene glycol per kilogram of water. And what we get is 10.7 molality, which is a little m. So now we've gotten to a point where we actually have a molality and molarity, and if we look, they are different. They're fairly similar, but they are in fact different. Now, last thing we want to do is figure out our mole fraction. For our mole fraction, we're going to start back at the 0.044 grams of ethylene glycol and the 0.600 grams of water, and we're going to convert both into moles to get us our mole fraction. So we have 62.07 grams of ethylene glycol per mole, and then we have 18.02 grams of water per mole of water. Multiply this out, we get a mole fraction of 0.194. And that is everything. End of the lecture. Hope you guys understood all that, and we will see you on Thursday.